Good afternoon, everyone. I think we can make a start. Uh, we are hoping to finish this topic. The topic will be error control, so that by tomorrow we can start looking at convolutional codes, and after that we can look at some uh, abstract algebra theory to see how it helps us to generate generator polynomials, or rather construct generator polynomials. Uh, so how we have just dealt with the cases whereby we already have a generator polynomial, a generator matrix. A matrix can be created from the polynomial, and uh, we already have to understand how this generator with a generator matrix, how you can generate a code which, once you transmit to the receiver, you are able to check whether it's actually what you transmitted or not, using a matrix which is related to the generator matrix, which we call a parity check matrix. And for every generator matrix, there's a corresponding parity check matrix, and that's what you use at the receiver. And that parity check matrix is such that it's transpose. If you multiply the generator matrix with the transpose, you get 0. Yeah. And I think it is that simple fact that makes it possible to detect errors, because I introduced the concept of the syndrome, and I said the syndrome R is given by uh, H by R dot ht, where R is the received code word, actually we don't like calling it code word, because code word means it was generated by that particular generator matrix. So we like using is a received sequence, received vector, because when you say the code word, already you're saying it has no errors. The code words are the 16 code words which were generated by the generator matrix. So what you're trying to find out is whether this received vector or sequence is actually a code word. You're not even checking whether it is the received code word. You are checking whether it's a code word. But how do we know that if it's a code word, it is a code word that was sent? We only know that because we know that to receive a code word from another code word, there has to be a minimum of 3 bit changes. A minimum. It may not result in another code word, but it may. If there are 3 bit changes, you may get another code word. And that's where the Hamming distance comes in. For you to be able to detect errors, and you can detect 2 errors, you need a minimum distance of 3. And when you have minimum distance of 3, it means actually you can be able to detect 2 bits in error, because you are 100% sure there is no way you can get another code word from a code word by changing 2 bits. But when you change 3 bits, that could give you another code word, and therefore syndrome decoding, or syndrome, well, you can call it decoding because you are detecting and correcting. Syndrome decoding will not work. That's why you need your code to have a minimum distance of 3, so that this can work. That when this is equal to 0, then you are sure the received vector is a code word. And if the minimum distance is 3 or more, we are sure that that code word is a code word that was transmitted. Yeah, I think we had covered that. Then another thing we talked about, now very important when it comes to correcting. You see, the syndrome up to now, when you try to find the syndrome and we find the syndrome in slot 0, 0 means 0, 0, 0. What it is telling us is that we have an error. But remember, this is not an error detection code. This is an error correcting code, which means not only does it detect, it also corrects. We don't have to go back to the receiver, to the transmitter. We can decode, we can correct without reference to the receiver. Sorry, to the transmitter. Yeah. Which works very well where you don't have a channel ask the transmitter to retransmit. Because there must be a channel for you how do you ask the transmitter to retransmit? Victor Musio. How do you ask the transmitter to retransmit? If there's an error. I haven't talked about it, so either you learned it somewhere or you can make a guess. What about the other Victor Muiruri? Oh, yes, somebody has a yes. Tell us.
Yes. You mentioned about the receiver should only send an acknowledgement if it was received, but if it wasn't received, there was nothing like the necessity for a negative acknowledgement. The transmitter will just know that it was not received.
Yeah. Thank you. That's a very good answer. What happens is the transmitter waits for an acknowledgement in the case where there is a return channel, and if there is no acknowledgement within a certain time, which the time which is set, it will be set according to the propagation time, transmission time. We are going to look at all those. What are they? Transmission time, computation time. Yeah, because there will be some computation at the receiver before you send back acknowledgement. So if it finds there is no acknowledgement after some time, there's normally a timer. You assume nothing was received and therefore you transmit again. But that only happens in the case where you are actually expecting an acknowledgement, where you have a return channel. Where you don't have a return channel, of necessity, the error must be corrected at the receiver. Yeah, thank you very much, Samuel, for that. Yes, Ogola.
Yes, I wanted to ask you about the formula. Should it be R or S? Because I've seen in getting the syndrome.
Oh, to get a syndrome.
Yeah, R is equal to R dot
Yes,
transpose.
it's R. Here, okay. You can call it okay. You can use any letter, but we choose to call it the R, the
The first
received
one.
the received syndrome. I mean the received vector.
The first one.
Oh, this
First
one.
R. Yeah.
S, the syndrome of R is equal to this.
Okay.
Oh,
Okay.
you're saying like I'm saying R is equal to this. No, I'm
Yeah.
saying S, comma, the syndrome of R is equal to this.
Okay.
Or
Okay. I also
S,
wanted
let's put
to.
into bracket syndrome of R. I see what the confusion was. Is
Okay.
equal to that. Yeah. Thank you for pointing out that.
I also wanted to ask whether you can determine the position of the error in the message using the syndrome that you calculated.
Yes, that's what I talked about last time, and now that's what I was coming to next. I was
Okay.
repeating it again. Now, once you get the syndrome, I think that's where we are. We are saying, to make sense, the syndrome, when you multiply this, okay, here what we have done the opposite. I said you can either use the um, the H with R transpose. That's what we have done here. Yeah, or you can use R with H transpose. The only difference it is going to give us, this one will give us a row, and this will give us a column. To give us a column of 3 zeros. Yeah, and this will give us a row vector, and this will give us a column vector. So you can use any of these. The syndrome will just be the orientation, it will just be the same syndrome. It can be this or this. Yeah. So trying to prove this point, I put it this way, it is easy to see it this way. Yeah. So we are saying this syndrome is, you see, this is the H. We can get it by multiplying it with R transpose. Now this R transpose, this received vector R, is simply the code word that was sent plus the error vector. And it makes sense. Let's say what was sent was something like, if we use a new example. And the problem I have is we have to work it out because we can't get it from that table. Because that table we agreed that the generator matrix starts with I'm talking about this table here. If you remember it, this table, the generator matrix starts with these bits. Starts with the pattern, and then it follows the identity matrix. Yeah, it starts with this pattern of bits and then identity matrix. So, but I think ours here. But you can see here, the generator matrix has identity matrix coming first. I think the important thing to remember is the identity matrix for the generator matrix and the parity check matrix must be opposite. Yeah. So the generator matrix for this would be 1 1 0. No. Would be 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 1 1 0 1 0 1. I'm just doing the transpose of this. Then 0 0 1, and this is 1 1 1. Oh, sorry, 1 1 1 1 1 1. So this is a generator matrix that corresponds to this parity check matrix. You can see the identity matrix are just opposite. So for the one here, it will be different. Actually, it was there. It was a different one. It was this one. You see? But here we are using this one. It's good always to be very conscious of that. Which again here I've changed. Sorry. I've kept on changing so it can be tricky. I've kept on no, this was the matrix. You can see our matrix here. This is on this side. So, and its parity check matrix is this one. So if you want to find out, for example, let's think about let's use a simple one. A very simple message to make our calculations easy. So if you multiply this one, this will become 1. Everything else is 0. Everything else is 0. Then this will become 0. Oh, it will become 1, sorry. And everything else is 0. So it will become 1. This will be 0 because of this 0. 0. You have to use this. Then that one will become then that one will become 0. Everything is 0. Of course, we expect this to be 1 0 0. Yeah, I don't like putting that. So we expect this to be 0 0 0 since it's systematic. This part will just produce this. Now it is this part which will be different. Let's see what this part will be. This is going to be 1 plus 0 plus 0 plus 0. So that will be 1. I'm just multiplying this with this. Then this with this will be 1 plus everything else is 0. and you as well put the commas. Right? It seems what is think of putting them. So this is 1, 1. The last one is 0. Yeah, because this is 0 plus all zeros. So this is our vector 1 0 0 0 1 1 0. Let's see. I will not come here. So you have 1 0 0 0 1. I'm putting it in the wrong place. 1 0 0 0 0 1 1. If you multiply this, it should give you a 0. Yeah, you can find out. Let's multiply this and this and this. This is 1 0 0 0 0. Something has gone wrong. We are getting 0. This is 1 0 0 0. Oh, was it 0 1 1 or 1 1 0? Oh, sorry. I can see where we are going wrong. One, 1 0. I'm just trying to produce this what we have calculated here. Yeah, so this is what we have received. I mean, we have generated this, we have transmitted, and we are assuming we don't. If there is no error, of course, this will be all 0. The error vector will be 0. Yeah. So let's assume there is no error. So we should get this 0. Yeah. And even if there is an error, this will be 0. What will change is this. If there is no error, this of course we expect it to be 0. And obviously there is no error vector. This will also be 0. Yeah. But let's see how this vector here is going to help us find out where the error is. So this, we are saying this is 1 plus 0 plus 0 plus 0 plus 1, because of these terms, 1 times 1 plus 0 plus 0. So 1 plus 1 is 0. Yeah. Yeah. You come to this row. So this will be 1 plus 0 plus 0 plus 0 plus 0 plus 1, because of this times this, plus 0. So it is 1 plus 1 is 0. Let's go to the last one. This is 0 plus 0 plus 0 plus 0 plus 1, because of this. Oh, the fifth one is 0. No, okay. Oh, this is 0 plus 0 plus 0 plus 0 plus 0, because this time this is 0 plus 0 plus 0. So this is also 0. So we are seeing when we receive a code word and we are assuming it has to be the correct code word, because you can only correct the error only when there is 1 bit changing. So it means it will be this, which is the correct one, plus one bit has changed. Let's say this bit changes. For this bit to change, it means the error vector is 0 0 0. Oh, this is the 1 1, because this has changed. We are saying this has changed. We are saying this one has changed. So that is 1. Then 0 0 0. So that when you add the 2, this will end up being 1. Yeah, I think that is clear to everybody. Now, let's multiply. We have seen this is 0. Let's multiply this and this to see what this will be. What will be. And you can see it's a no-brainer because of this 1 which is here. When you multiply, it will always give, let's see, let's actually multiply. This is 0 plus 0 plus 0 plus 1. See, this is 1 and everything else is 0. So it's giving, because of this 1 being in the fourth position, actually you're going to find out that that 1, let's not jump the gun, let's see what we are going to get. That is 1. Let's multiply the second row. This is 1 plus, that is 0 plus 0 plus 0 plus 1 plus 0 plus 0 plus 0. That is 1. Let's do the last row. This is 0 plus 0. I'm just multiplying. I don't know how to repeat this. I think everybody understands how you multiply that. But just in the event there is one who is not sure, let me do it again. Yeah. Yeah. So again, so this will be 0, but because of this 1 times this 1, it will also be 1. And you can see from this, you can see this one is actually this. Yeah. And what is that telling us? The syndrome gives us the position of the error. So the error is on the fourth position, because to get this, the position from here, 1, 2, 3, 4. The position of the error is 4 the bit. 1, 2, 3, 4. And you can see clearly if this is 0 and this is 1, which means the error is here, you're going to get this. You can do that. If this is the one which is 1, you're going to get this. So you can see you can only correct errors only when 1 bit is in error. Because if 2 bits are in error, then here the syndrome, again, this syndrome decoding will not work. Because it will not give you which row. Yeah. So what normally happens, the receiver has a lookup table of where the error is. So the lookup table will be 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Yeah. I will write here 0, 0, 0, 1. Yeah. So that will be the lookup table. And the receiver, whenever the receiver gets an error, it will compare that syndrome with this, and it will tell it, okay, this must be bit 1 in error, bit 2, or sometimes you like calling it bit 0. Let's call it just bit 0. In digital communication and computing, we always use bit 0 to bit n-1. Yeah. So this is bit 1, bit 2, bit 3, bit 4, bit 6. That's 6. So bit 4, bit 5, and bit 6. Yeah. You can see there is no 0, 0, 0, because when it is 0, 0, 0, we know there is no error. Yeah. So there could be just 0, 0, 0, no error. Yeah. Yeah. So this is how syndrome syndrome decoding works. Yeah.
Yeah, excuse me, Sally. In other texts, I saw that they were using the H transport as the lookup table when once you calculated the syndrome. How true is that assertion?
Yeah, actually, that's what we are saying. This is what it is. This is a lookup table. It's actually H transpose. Yeah, this is H. This is H transpose.
Okay.
Yeah. Thank you. Yes.
Yes, I just wish to seek a clarification.
Yeah.
Because from what I understand is that we get the vector, the received vector is what the receiver gets.
Yeah.
So how exactly will the receiver know that the error vector has a, let's say for the case we've done, that at a certain position we have a 1, so that we can get the syndrome as maybe 111. How exactly does the receiver know? How is the error vector?
No, it doesn't know what it does. This receiver has a name. What do you call it? A multiplier. Yeah, it just multiplies. It has a vector multiplier. It just multiplies this vector with what it has received. I mean, with the you're saying you're saying how does it get this? It doesn't know. See, it has gotten this. It doesn't know what was sent, but it has received some vector, which is this one. So it simply takes the syndrome, multiplies with this transpose, and then it gets this. Alternatively, it can take the vector, multiply with H transpose. Yeah. Whichever it is, either the vector with the H transpose or H transpose, H with the received vector transpose. So when it multiplies, it will get this. I'm saying it is getting this because if the vector is this one, if the vector is different, it will get something different. So what it's going to do, it will go to the lookup table. Yeah. You try to see this one corresponds to each one. In fact, normally what it will do is it will just get this one and have a way of it might just compare actually. Then it will compare this one and this one, find whether there is a distance. If there is no distance, which means they are the same. Yeah. You compare with that one, compare with that. If you compare with these ones, actually this one doesn't compare because the moment it gets this 0, it does not need to refer to this table. If it gets all zeros, it doesn't even need to go to the table. It just receives the vector, goes ahead to remove the error checking bits, and then recover the original data. Yeah. In the event, it's not 0, 0, 0, this syndrome. Yeah. Because we are saying the syndrome is actually, I was only separating these two to show that the syndrome is a combination of a correct code word and an error vector. So this is due to this. We're getting this due to the error vector. So what it is actually receiving is one sequence. Yeah. So it will get this sequence, multiply with this, then it gets this, then it's going to compare this with this. Whatever methods you use to compare, but of course the easiest is just to check the distance. Yeah. Look at whether their positions are the same. Only this will give you a distance of 0. Yeah. Then it gets this one giving distance of 0, it will see, oh, bit 3 is problem. What is a bit 3? All it has to do is whatever it had gotten, it will just flip it. So, for example, you see, in this case, for you to get this, what you have received is this. You have received this vector. Yeah? For you to receive this, you have received this vector. So this is all. That's why this is 1. So you have received this vector, which is an addition of this one plus this one. You have received this vector. Yeah, that's when it will receive this. Yeah. So what it will do, it knows because of this bit 3 is in error. It will simply flip bit 3 and accept that as the correct code word. And you can see it will not work. If, for example, there were 3 bits that ended up giving you the correct code word, then it will be wrong because it will decode, it will not decode correctly. If there are 3 bits in error and therefore it received another code word, because in that case, the syndrome will be 0. But there's an error. So if there are errors which are more than 2 bits, you're going to get some errors. Yeah. You're going to get some errors, and what will happen is your error checking mechanism will have failed. And therefore you're going to get good results. But for most of these systems, to get more than 3 bits of an error, that channel is a terrible channel. You should not even be using it, because then what will happen is there will be a lot of retransmissions, and especially you see like this one, there is not retransmission. Yeah, because we are thinking this could be a broadcasting channel where we expect to correct things at the receiver. Did I answer your question?
Yes, it's clarified. Thank you.
Thank you very much. So we talked about the minimum distance of a block code. I think I explained last time. It's a very important concept. So for this code, it has to have a minimum distance of 3, and you can see the reason why, because 3 is very far. With a short distance, it means you could end up getting a code word, and therefore syndrome decoding will not work. Yeah. The other thing we need to know is the minimum distance of a linear block code is equal to the minimum weight of its non-zero code words. A very simple statement, a very important one, because it means to find the minimum distance, you don't need to compare each and every code word with the other code word. All you have to do is actually look at the minimum weight, and you know the weight is the number of ones. So you just look at the one which has the least number of ones. That's the minimum weight, excluding the 0 code word, because again you can't do that with the 0 code word, because the minimum distance between the 0 code word and all 1 code word is 7. Yeah. Yeah. Actually, I don't even know why you are excluding it, because this will be maximum. But normally we exclude the 0 code word. I tend to think, why do you exclude the 0 code word? Because the zero code word will just give us a greater figure. Yeah, because this will be a maximum distance. But anyway, whenever we are working out the minimum distance, we don't consider the zero code word. I'm trying to see why. Because that will give us a distance which is more. So again, it will not be really, to give us more weight. Oh no, sorry. Of course, I can see why, because we are talking about minimum weight, and of course, this non-zero code word has zero weight. Yeah, so it has to be minimum weight, excluding the zero code word. Because the zero code word has zero weight. Yeah, so this cannot be true if the zero code word is included. So I think we have just explained the error correction with what I have done here, the syndrome decoding. And this is just explaining what we have already talked about, that a T error detecting code has to have a minimum distance. So it means if T is 1, then okay, this one, if T is 1, then minimum distance needs to be 2, because just 2 minus 1. If T is 2, this has to be 3, like the one we have been dealing with. Yeah. So this is the relationship between error detection capability and the minimum distance. And between the error correcting capability and the minimum distance is this one. The mean minus 1 divided by 2. I think we talked about that one last time. So unless there are any questions on that. Now, there's another class of binary codes which have a block length of n is equal to 2r to the minus 1, and a message length of k is equal to the r minus 2 to the r minus 1, for r is equal or greater than 2. What you are saying n, because the codes are normally nk, yeah, it means you can have a Hamming code so long as r is equal to greater than 2. If r is equal to 2, then n is equal to 2 to the r, which is 2 to the power of 2, 4, minus 1. So n is 3. And k is equal to 2 to the r minus 1. So 2 to the r is 2. No, it's 4, sorry. Because you are saying it has to be 2 or greater. And r is 2, so 4 minus 2 becomes 2, minus 1 becomes 1. It's a 3, 1 code. But normally we don't. So actually this should be, I think I should change this. It should be greater than 2. Yeah. Because this one, from this definition, is qualified to be a Hamming code. But if you're having 1 bit with 3 bits, very likely this is a repetition code. Yeah. You have 1 code and producing 3. I mean, you have 1 bit, and to transmit that 1 bit, you're using 3 bits. Yeah. So, but this class of bits, I mean, this class of codes, they are called Hamming codes, and they are able to detect 2 bits in error and correct 1 bit. Yeah. 2-bit errors or correct 1 bit. So, but anyway, the formula goes the way it was, but I think what I've seen with most textbooks, they still refer this, which means even this representation code could qualify as a Hamming code, yeah, by this definition, yeah. Otherwise, the practical Hamming code is a 7-4 code, where R is equal to 3, yeah. So N is equal to 2 to the 3 minus 1, which is 7, and K is equal to 2 to the 3, 8, minus 3, 5, minus 4, minus 1, 4. So that's the smallest Hamming code, without considering this, which basically is a repetition code, and very inefficient. To send one bit, you have 3 bits. But it is still considered to be a Hamming code. But the practical Hamming code, I think the smallest is this 7-4. Yeah. So now so the next one is this is equal to 4. So we are going to see, I think it's going to be 15, 11. I'm not sure. That is the next Hamming code. Yeah. And we are going to see how you can create a simple. We are going to look at a simple algorithm for. We have 8 minutes, and I want us to finish this. I think it's 50, so. This is 2 to the 4, 16 minus 1, 15. Then 2 to the 4, 16 minus 4, 12 minus 1, 11. So this is the next Hamming code. So these Hamming codes have that characteristic that this is the relationship between N and K. All Hamming codes have that relationship. Yeah. And we are going to see how you produce these Hamming codes. Yeah. So the entanglement must obey this, as I already told you this, that the generator and the H transpose must obey this rule. So for a 7-4 non-systematic Hamming code, you can use this algorithm below here. It's a very simple algorithm. I think we can finish in the remaining minutes. So this is how it works. Error correcting bits are chosen such that the XOR of all bits containing a 1 is 0. The error checking bits are placed in positions which are powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. The message bits are placed in the rest of the position. So what we do, I think I can just go to how this is what you have. Let's say we want to work with a 7-4 Hamming code, which means you have written D1 to D7. Yeah, I think this one, for this one, you must refer to D1 to D7, because this is what we are trying to do. The algorithm was trying to employ. We will not work with the D0 to D6. Yeah. So D1 to D7. So what you do is you place your bits in that order. Yeah. When you place your bits here, or rather, actually, what you do is you place your error checking bits in the positions which are powers of 2. Yeah. So the first position here is always, this is the first position. That will be 2 to the 0. The second position where there will be a bit is 2 to the 1. Then there will be 2 to the 3, 2 to the 2, 2 to the 3, like that. But you can see for 7-4, you won't reach 2 to the 3, because 2 to the 3 means there's a nth position. Yeah. So for 7, 4, you only have this. So you have it here, which is 2 to the 0. You have it here, 2 to the 1. Then you have it here, the fourth position, because of 2 to the 4. Yeah. So you place the error checking bits there. And we don't know what this error checking bits is. All we are saying is leave those spaces for the error checking bits. You are going to calculate them. Then you take your 4 bits, which are your message bits. So you have this 1, 0, 0, 1. These are your message bits. Now you want to generate these bits from the message bits. And then transmit. Now you transmit what you get. Already this is calculated. Otherwise, these are the message bits. So what we are doing, we are saying the parity bit 1, you receive it by ensuring that whatever is in the first position, in the third position, in the 5th position, and 7th position, when they are added, they will add up to 0. That is what you're trying to do. They will add up to 0. And you wonder, how do you get those positions? How you get those positions is from here. So you want to find out the first position is here. So if you write this 1 to 7 in binary, you're going to see that the places which have 1 at this position are the ones you are considering. 1, 3, 5, and 7. So for this position, you are going to consider this in the positions in decimal, and you write it out in binary, and the ones which have got 1s at this place in this first position are the ones you are going to consider for this. For this position, you are going to consider the ones which have got 1s in this position. So you are going to consider 2nd position, 3rd position, 6th position, and 7th position. And for this position, you're going to consider the ones, the easiest way to look at it is the ones which have got bit position, same as 4, this position here. So you can see that will be 4, 5, 6, 7. This one. So if you use that formula, you are going to find, let's find the first one. We want to know what one should be. So what do? We know 3 is a 1. 5 is a 0. 7 is a 1. Yeah? So it means this is 1 plus 1. I mean, this is a 1. Oh, yeah, 7 is a 1. So it is a 1 plus a 0 plus a 1, which is a 0. So it's already a 0. Actually, it's a parity thing. This is already a 0. So this has to be 0 so that this remains a 0. Because this is, for this case, this is 1, this is 1, this is 0. So this has to be a 0 for it to remain 0. Let's go to this position. This position, 2 is a 0, 3 is a 1, 6 is a 0, 7 is a 1. So this is a 1 and the 1. Oh no, 2 is not a 0, sorry. We don't know what it should be. Sorry, I'm already, this one is, you are trying to get from the ones which you have. So 3 is a 1, 6 is a 0. 7 is a 1. So 1 plus 1 is 0. So for you to retain 0, this has to be 0. Then you look at the last one. 5 is a 0. 6 is a 0. 7 is a 1. So for this to become a 0, this has to be a 1. That's why we are saying this is a 1. So this is what you are going to transmit. Yeah. And this algorithm will still work with the next Hamming code, which is a 1511. Because you'd have 4 bit positions. Yeah, because there are 15 bits, 11 are message, so 4 are error checking bits. So the error checking bits will be in this position, this position, this position, and now this position, the 8th position. Yeah, this will be the error checking bits. Yeah. So this is, oh, sorry, it's a minute. Can we spend another 2 minutes to finish this? Just another 2 minutes. So this, you wanted to send this, you wanted to transmit this sequence 1001, 1001, but you end up transmitting 1001, 100. Yeah. So this is what you end up transmitting instead of this. How does it check errors? It's very simple. You do the same math at the other end. And what happens here is, let's say this bit changes. Let's say this bit changes to 0. D4. If D4 changes, you can see it only affects this position. Yeah? It only affects this position. So if for example, D4 is changed, what you'd get here would be a 1 and a 0 and a 0. And actually that tells us it is the 4th position. You read backwards, 1, 0, 0. If D4 changed, because it was 1, it changed to 0. Of course, if this changed to 0, this will be 1. But others won't change because there is no 4 here. So they won't change. Yeah? Let's see. Suppose something else changed. Actually, I can remove all these so to appreciate what's on. But you can see whichever position changes, it will be given by the position of what has changed, will be given by just reading these bits from this end going backwards. And it makes sense is because of this, the order is going from D1 to D7. So you'll be reading from this end. So ensure that you have sent your yes, somebody has a question.
Could you repeat how you determine the error checking bits for like maybe the 7-4 Hamming code?
How you check the error at the receiver?
No, how you determine which bits are going to be the error checking bits.
Oh, yes. It's you choose the positions you choose, the powers of 2. The powers of 2. So what would happen is you choose 2 to the 0, 2 to the 1, So 2 to the 0 is first position here, D1. 2 to the 1 means this position. 2 to the power of 2 means the fourth position. So, of course, for a 7-4 Hamming code, those are the only positions which have error checking bits. For a 1511, which is the next Hamming code there, it would have now also the 2 to the power of 3. It would have another checking bit in the 8th position. But what we are doing, we are saying how you determine that is you use these positions. But the positions, how do you get the positions? You can get them from here. You can remember this, but there's no point of remembering this because these positions are derived from this. We are saying the first position is 001. So 1 in decimal is 001. 2 in decimal, 2 in decimal is in binary is 010. Like that and like that and like that. So now you're going to find that the error checking bits are in these positions. First, second, and the fourth position. And we are saying for here, this has 001. Okay? You see the good thing about when you talk about these positions, it means I have only one. Yeah? 1 has only 1. The others are zeros. 2 has only 1. The others are 0. 4 has only 1. The others are 0. So we are saying the ones which have got bits, 1 bit, where 1 has a 1 bit, go together. You see, so 1 has a 1 bit here, so it goes with 3, which has a 1 bit here, and this one which has 1 bit here and here. So we are saying to get these 3 must add to 0. Or rather, what we are saying, we are using even parity so that their positions add up to 0. It's a way of calculating the even parity. Yeah. So we are saying for them to add up to 0, and already you have these 3 positions. See, the positions you're using here are the ones which have the bits, and you have already given those 3. What does it have to be so that this is 0? You are given this and this and this. What does this have to be for this to be equal to 0? You are given here and here and here. What does this have to be for this to be equal to 0? That is a simple, very simple principle. It means you are using even parity. Because that's the parity you are going to check also at the receiver.
So, like, how would this change if it was the 1511 Hamming code?
If it's an 11, what will happen is you are going to use, I'm trying to calculate 11. So this is 7, let's add here. Another 4 position. Oh, no. Of course, these are not, they are 15. Sorry about that. So I will have to add more. 15, I have to add 8. They would fit here. The base there is completely to another one. Divided into 2, and this has, okay, this one has 7. One, 2, 3, 4, 5, 6, 7. Then this one has 8. Yeah, like that. So that one would mean this position is for error checking bits. This position is for error checking bits. This position is for error checking bits. The other position will be 1, 2, 3, 4, 5, 6, 7, 8. And this is for error checking bits. So now for the data, you use this one, this one, this one, this one, this one. At the time you are getting 11 of them, is this? This one, it means you can't use this one. This you have said these are error checking bits. So you use that one, that one, that one, that one, that one. So this I get 11th position. 11 position. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11. So this will give you, you wanted to send those 11 bits, you end up sending all these 15 bits for the purposes of checking the errors. And you can only correct only one bit again. Is that okay?
Yeah, it's fine.
Okay, thank you very much.
I have a question.
Yes.
Since now the Hamming bit can, well, you say detect 2 errors and correct 1.
Yeah.
And also the simple parity could, I believe, was detect 1 error. Why choose the Hamming? I'm seeing it's taking a lot of space for the data.
Oh, I think it's just that the Hamming code is easy to design, because when we come to this Hamming one is even what we have been dealing with. So long as the distance is 3, this Hamming code, if you create this Hamming code, it will have a distance of 3. But you can have other block codes which have got a distance of 3, minimum distance of 3, which correct also one error, 1 bit error. But we are going to see later that there's a class of codes which use algebraic codes, algebraic structures, where you can be able to actually detect and correct more errors. You can choose so we are going to see. So in fact, these are not normally used in error checking mechanisms. So you find the ones which are normally used mainly error correction mechanisms are things like the BCH codes or Reed-Solomon's codes, which are very similar. They're generated very same. They are constructed using almost the same principles, and they are able to correct very many errors. Yeah, perhaps Reed-Solomon. If you read, you are going to find Reed-Solomon is used in CDs. There's a Reed-Solomon that was used with the Voyager, because that transmission is very fast, so we expect a lot of errors if you're transmitting from the Voyager to the Earth. So it's also used. So these ones that only detect 1 error and correct 2 errors, you are right, they are very inefficient. Especially if to send 4 bits, you require another 3 bits. That's a lot of inefficient if you want to correct. So for error correcting codes, it's unlikely that you'll be using this. Yeah. But I think we still use it for learning. It's one of the simplest code to understand. Is that okay, Samuel?
Yes, thank you.
But in reality, it's very, very inefficient. Yeah, so in reality, we tend to use like in a BCH codes and like in the Solomon's codes. But CRC is used a lot for the detection. CRC is used a lot. In fact, it is used in Ethernet for checking errors. Yeah. So, but this Hamming codes, I think now that they are BT code, nobody uses this Hamming code. Although actually a Hamming code can also be considered to be a single error correcting BC, a special case of a single error correcting BCH code. Yeah. You can be considered to be that special case of that. Yeah. So I think we'll stop there. We meet tomorrow, where we will continue with convolutional codes. I'll send you the notes for convolutional codes. So have a good day and